Okay. So I hope you can hear me. So let us start today's discussion. So I told you that in this part of the board is visible. So I have in the previous lecture I have told you, given you the notion of pole. What is a pole? First of all, I have told you what is a singularity. Then I have mentioned what is a pole of order k, a simple pole which is a pole of order 1, and then I have told you what is isolated singularity. Isolated singularity basically means that there is a singular point, there is a singularity in the function, the complex variable, but around the neighborhood of that point, the function is completely analytic. At all points around the neighborhood of this point, the function is analytic. Then it is called an isolated singularity. If it is not analytic around the neighborhood also, then it is not an isolated singularity. So we have seen the notion of such a thing, and then two important things about the notations and things like that. I've told you what this is. This is very important. This is basically the notion of this neighborhood around the point z0. It basically means that it is the set of all points z such that z minus z0 is less than r. So this is something very important. This is sometimes called the delta neighborhood also. So where delta neighborhood basically means that you replace this r by delta. So this r is basically the radius. So you have this point z0, and this is the radius r, and this is a set of points in this circle, but points which are not on the circle. So this notion is something, the notion of a neighborhood of around a point. This is something very important. And also I gave you the notion of this punctured disk. This is also something very important. This is the same as an open annulus whose center is 0, z0, and it is denoted by this. This thing and this thing, these two things are the same thing. So this is the open annulus. So it basically means that this is the set of all points such that 0 So what it means is that you have taken out this point z0. So this is the notion of the punctured disk. And then you also have this thing, an open annulus. So for r less than r, so this is the notion of the open annulus. So we have, so this is denoted by this thing, and this is nothing but the set of points z which satisfies this inequality. So this means that you have this thing, this circle, which is centered around z0, and this is radius small r, this radius is capital R, and the set of points belongs to this annulus, this region, the shaded region. But the points do not lie on this inner circle as well as the outer. It does not lie on the boundary of the of this one, and also the boundary of the outer circle. It lies only in this annulus. So this is the notion of the open annulus, and the closed annulus is just denoted by this a bar, which basically tells you that all the points are included. The points can also lie on this circle, it can also lie on this circle, and all the points inside this annulus. So this is the notion of the closed annulus. So these are some notions that we have introduced: the delta neighborhood, the punctured disk, the open annulus, and the closed annulus. So these are very general. These are used in various places in mathematics. In pure mathematics, for example, in functional analysis, metric spaces, topological spaces, whatever it is, vector spaces, you will find that these notions are very, very useful. In real analysis, complex analysis, whichever branch of mathematics you are looking at. So now, today what we shall first of all do is look at some simple examples. So the first example that I shall show you is fz is equal to sine z by z cube. Let us take this as the first example. Okay. So this is our example 1. So what we shall do, we shall look at the singularity structure of this function. So you know that sine z, in fact you can see it from this thing itself. You know that sine z has an expansion like this. I hope all of you are familiar with this expansion of sine of z. Okay, and this gives us 1 by z square minus 3 factorial and so on. So this is what we have. Okay, and therefore, can you say what is the pole structure or the singularity structure of this function f of z? It is immediate. You can see that this is a pole of order 2. This has a singularity. This function f of z has a singularity at z is equal to 0. So this is singular at z is equal to 0. The first notion that I have introduced, that of singularity of a function. So you can see that at z is equal to 0, it diverges. Okay, this is the first thing. But now, diverges how? So you must say what kind of a pole it is. A pole also means a singularity. Let me remind you of one more thing that I discussed in the previous lecture, and that was the Laura series expansion. Is it visible? Can you see this on the top?
Yes, sir.
Okay,
yes,
good.
Yes,
very good. So, if you remember, on Monday, we discussed, we have not proved this rigorously, but this is the Laura series expansion of a function. So, it tells you that if z0 is a singular point of this function of the complex variable z, then you can have a Laura's, you can expand the function around that point z0, but you should remember that that particular point should not be included in your expansion. It basically means that if you include that point in the expansion, then the series will diverge. So it basically tells you, so if you just expand this thing, this expansion in longhand, what you will get is something like this. Then C of minus k by z minus z0 to the power of k plus C of minus k plus 1 by z minus z0 to the power of k minus 1, and so on. And then you will have C0 plus C1 z minus z0 and so on. And here you will have a term like this, plus dot 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 plus C minus 1 z minus z z0. And we said that this function of the complex variable is said to have a pole of order k if all the coefficients Cn vanishes when n is less than minus k. So all the terms from this side, if I go to the left, So all these terms have n, the value of n for all these terms is less than minus k, right? So if all those coefficients vanish, then the function is said to have a pole of order k. The singularity structure is a pole of order k. And you can see what is happening here. You can see that it has a pole. This is a LoRa series expansion. You can see the form is like a LoRa series expansion. And therefore, this has a pole of order 2. Because all the terms, the coefficient of 1 by z cubed term, if I go like this on the left hand side, all the coefficients vanish. And therefore, this has a pole of order 2. So this is one example, a very simple example. Let us take one more example. And obviously, if I ask you that what is the value of C minus 2? What will be the value of C minus 2?
1.
Very good. C minus 2 is 1. And you can see that if you go C minus 3, so n is less than minus 2, right? So C minus 3, C minus 4, and all the subsequent terms, if I go on the left hand side, all the terms are 0. They vanish. Okay? Now let us take an example. Example 2. This is f of z is 1 by z e to the power of z. And see what is the pole structure. This is very simple actually, because you can just expand this. You know the power series expansion of the exponential function. You keep on doing this. And therefore, the first term will be 1 by z plus 1 plus z by 2 factorial plus dot dot dot. And therefore, this, you can see that this is the LoRa series expansion of this function. And this has a simple pole, that is a pole of order 1. Because all the terms, all the coefficients of terms like 1 by z square, 1 by z cube, all those coefficients vanish. And therefore, this is a pole of order 1. It's a simple pole. At which point is this function singular? Once again, it is z is equal to 0. This is the singular point of this function. Let us take a third example. F of z is equal to z sine of 1 by z. This is very interesting. This particular function is quite interesting, z squared. And let us investigate the singularity structure of this function. So this is z squared. What will be this one? This will be 1 by z minus 1 by 3 factorial, 1 by z cube plus 1 by 5 factorial, 1 by z5. Right? Is it okay? Is this okay? You just expand it. Okay. And then you just multiply this out. If I multiply this full thing by z square, then you will get z, get 1 by z, z cube, and so on. So you see that in this case, this is the LoRa series expansion of this function. And the singularity is obviously at z is equal to 0. So once again, the singularity is at z is equal to 0. But what kind of a singularity is this? This singularity is an essential singularity at z is equal to 0. Why? Because all the coefficients, all the negative powers of z, all of them exist. None of them vanish. Obviously, 1 by z squared term is not there, but it keeps on going in the negative side. And therefore, this is an essential singularity of the function, this function, z square sine 1 by z at z is equal to 0. Okay? If you look at the definition of essential singularity, then you can classify this particular singularity in the essential category. So these are the three examples. We can give some more examples. We can keep on going, giving many examples. For example, you can take another example, example 4. This is our example 4. F of z is equal to e to the power of 2 by z. And since these functions, you should remember one more thing, that since these functions have singularities, therefore they are not analytic. They are not analytic functions. Okay? They are not differentiable at z is equal to 0. Let us take this function, f of z is equal to e to the power of 2 by z, and you can just power series expand this function. This will be 1 plus 2 by z plus 1 by 2 factorial, 4 by z square, and so on. This is the Laura series expansion. It has a singularity at z is equal to 0, and the negative powers keep on increasing as you go. Therefore, all the coefficients in the Laura series expansion on the negative side, they are non-zero. It goes on like this, and therefore the singularity at z is equal to 0 for this function is an essential singularity. Okay? Let us take another example, a simple example, and see and investigate what is the pole structure of that function. So this is example 5. Let me take g of z is equal to 3 divided by 2z plus z square minus z cube. Let us investigate the pole structure of this function. So what will you do? How will you proceed in order to find the pole structure? When I say that you need to find out the pole structure of a function, what I mean is you have to find out at which points the function is singular and what is the order of that pole, of that singularity. Or is it a pole of order k, or a simple pole, or an essential singularity, and so on. So you have to find these things. So here I can just take z common. This is very simple algebra. So you get something like this. Then you can factorize this part. I just leave it as an exercise for you to factorize. It's very simple. You have learned it in elementary school, in school algebra. So if you just factorize this, then you will get 1 plus z and 2 minus z. So what is the pole structure of this function? It is very simple. There is a pole at z is equal to 0. There is a pole at z is equal to -1. And there is a pole at z is equal to 2. Z is equal to 0, -1, and 2. And what is the order of these poles at these points? These are all simple poles. So these are simple poles. So poles of order 1. Simple poles. So poles of order 1. These are the points where the singularities are, and the singularities are all simple poles. Is this okay? Is this point clear? Are these examples clear to you?
Yes.
Good. Okay. So now I will introduce another concept today. This is also very simple, it's not difficult. And that is the concept of a residue of a complex function. So it means that obviously when we talk of residue of a function of a complex variable, then implicitly we assume that the function has a pole at some point, and you want to calculate the residue at that pole. You want to calculate a value at that pole, and that value is called the residue of the function. So let us just introduce this notion now, the notion of a residue of a function of a complex variable. So for that, first of all, what we would need is we would need the Laura series expansion. And the Laura series expansion of a function is something like this, z minus z naught. So it has a pole at z naught, z is equal to z naught. And therefore, since it is a pole, therefore you have to, if I want to expand the function around that pole, around that singularity, then the expansion that one has is the Laura series expansion of the function. Is this, yes, it is visible, c minus 1. So this is the full Laura series expansion of the function of a complex variable f of z, which has a singularity at z is equal to z naught. This is a singularity at z is equal to z naught, so this is the Laura series expansion. And what is the residue? How is the residue defined? What do I mean by the residue of a function? The residue of the function of complex variable f at the point z naught is denoted in this way. Residue, you write it in this way. Residue bracket f comma z naught. So it means you are calculating the residue of the function at the point, at the singular point z naught. And therefore, and this is defined as the coefficient of this power of z minus z naught. So it is by definition nothing but c minus 1. So this is how you define the residue of the function at z is equal to z naught. This is what we mean by residue of a function. And let us now, once again, we will see some examples, one example. But before that, let me give you some theory about these residues, because this is a very important notion, which is very important in evaluating integrals. So you have something in complex analysis which is known as Cauchy residue theorem, and I told you that I proved this result. If you remember, I proved this result: f of z, z minus z naught, that is 2 pi I f of z naught. If you remember, I derived this result from the Cauchy integral theorem. If f of z is an analytic function in the region R bounded by this simple closed contour C, then the contour integral of f of z on this contour divided by z minus z naught is 2 pi I f of z naught. So this, I told you that this result is actually related to the Cauchy residue theorem, but for that we need to have the notion of, we need to know what is the residue of a complex function. So this result is also important actually related to the Cauchy residue theorem. So let us first of all consider the case of a simple pole. And let us calculate, suppose z is equal to z naught is the singularity of this function f of z, and let us suppose that this singularity is a pole of order 1, that is a simple pole. Therefore, what we will have f of z, the Laura series expansion will be c minus 1, z minus z naught, because all the other terms on the left hand side will go to 0. Since this is a simple pole, there are no powers of higher negative powers of z minus z naught, and then we will have c naught plus c1, z minus z naught plus dot dot dot. So this is the Laura series expansion, because this is a simple pole. And what we need to find is, we need to find this coefficient, because this coefficient is a residue of the function. Okay, so let us find a formula for this coefficient. It is simple to find it out. What we shall do is, we shall multiply throughout both sides of this equation by z minus z naught. So if you do that, then this will be c minus 1 plus c naught z minus z naught plus c1 z minus z naught square plus dot dot dot. Okay. So what I have done is multiply throughout by z minus z naught, and therefore we get this equation. Now it is simple. You just take limit z going to z naught of this full thing. Just take limit z going to z naught of this expression, and in that limit, if z goes to z naught, then all these terms are 0, right? These terms vanish, because these are all positive powers of z minus z naught, and therefore c minus 1 is basically this. And what is c minus 1? C minus 1 is nothing but residue of the function at z naught, by definition. Therefore, if the function has a pole of order k at z is equal to z naught, that is, it is a simple pole, then the residue of the function at z naught is given by the formula this. It is limit z tending to z naught of z minus z naught multiplied by f of z. So this is a very important expression in order to evaluate the residues of functions. Let us now, you may ask the following question, that this is for a simple pole, but what about poles of order k? That is, if the pole is a pole of order 2 or pole of order 3, then what will be the formula? Then we should, so let us find out a formula for the residue of the function for a pole of order k. Okay, so for a pole of order k, f of z will be c. Since this is a pole of order k, therefore the Laura series expansion will be something like this. Okay, the pole of order k at z is equal to z naught. Therefore, the Laura series expansion of the function is this. Do you agree? Is it okay?
Yes, sir.
Okay, good. So now, once again, I want to find out a formula for this coefficient. This is our goal. We want to develop a formula for this coefficient, because this coefficient is by definition the residue of the function at z naught, at the singular point. So what should I do? Once again, let me multiply both sides of this equation by z minus z naught to the power of k. Let us multiply this. And what we shall have is c minus k plus c minus k plus 1 z minus z naught plus dot dot dot. Then we will have plus c minus k z minus z naught to the power of k minus 1. Is it clear? Because we are multiplying both sides of this equation by z minus z naught to the power of k plus c naught Is it visible? Okay, I think it is. Okay. z minus z naught, power of k plus 1, and so on, and higher order powers of this. So now, but our aim is to find this coefficient. So now, in order to isolate this coefficient only, what we can do is differentiate both sides k minus 1 times. Let us differentiate both sides of this equation k minus 1 times. So if you differentiate both sides of this equation k minus 1 times, then you can see this term under differentiation goes away, this goes away, all the terms on the left of this c minus 1 vanishes, because the derivatives from this is of order k minus 2 and less, and you are differentiating k minus 1 times, and these powers are less than k minus 1 times of differentiation. Therefore, all these terms on the left, they vanish, they are gone. And this will give you what? If I differentiate this term k minus 1 times, what will you get? You will get k minus 1 factorial c minus 1. And you will have terms, this all these terms, these particular terms have powers which are more than k minus 1 times of differentiation. And therefore, all these terms after differentiating k minus 1 times with respect to z will have some z minus z naught. All these terms will have some positive power of z minus z naught. And therefore, it is very simple. You just take, in order to get rid of those terms, you take limit z going to z naught. So if I take limit z going to z naught, then all these terms, they have some positive power of z minus z naught. All these terms will vanish. So all these terms are gone. In the limit z going to z naught, and therefore, now you have the nice formula. You have a nice simple formula now. That c minus 1 is equal to 1 by k minus 1 factorial limit z going to z naught of d k minus 1 dz k minus 1 of z minus z naught to the power of k f of z. So this is the what is c minus 1 by definition is residue of the function f at z naught. By definition, c minus 1 is residue of the function f at z naught, and this is the formula for calculating the residue of the function at z equal to z naught. And you can immediately check that what happens if I set k equals 1. Let me set k equals 1. So k is equal to 1, it basically means that this is a pole of order 1. It is a simple pole. So k is equal to 1, k minus 1 factorial is 0 factorial, 0 factorial is 1, so this factor is 1. K equal to 1 means this derivative is no longer there, because this is d0, dz 0, so this derivative is no longer there. So it is just limit z tending to z naught, z minus z naught, this power is 1, z minus z naught of f of z. You recovered the formula for the residue of the function for a simple pole, for k is equal to 1. If I set k is equal to 1 in this general formula. So this formula actually captures the formula of the simple pole also. So this is the most general formula if the function has a pole of order k. Let us now do an example and see what we get from this theory that we have developed so far today. The theory of calculating residues of a function. So let us take this function f of z is equal to 1 by z square plus 4 whole cube. Let us take this function. What are the poles of this function? So poles of this function, in order to find it, we have to set z square plus 4 is equal to 0. And this will give us what? Z is equal to 2i. Actually, the poles are at plus minus 2i, but let us take the pole 2i. And what is, so there are poles at z is equal to 2i. And what is the order of this pole? The order of this pole is 3. It's a pole of order 3. So this is a pole, this z is equal to 2i, this is a pole in the upper half plane, upper half complex plane, right? And this pole is a pole of order 3. Similarly, you also have a pole in the lower half of the complex plane at minus 2i. And that pole is also of order 3. Let us now calculate what is the residue of this function at the pole 2i. So this is our problem. Since this is a pole of order 3, apply this formula for pole of order 2. So what is k? K is 3. Therefore, k minus 1 is 2. So I have 1 by 2 factorial. Limit z goes to 2i b of what? Just a minute. I'm just. I actually have to go for the annual evaluation today, but let me finish this example and then leave. So you can simply see that this will be d2, dz2, and then we will have z minus 2i cube, and then the function is z square plus 4 cube. And you have to calculate this. Okay? So how will you do this? Hello? জানিব না হ্যাঁ ওই ফার্মিয়নটা করে দিন, আমি ফার্মিয়নে বসবো। হ্যাঁ আমার ক্লাস আছে, এখন ক্লাস চলছে আমার। না আমি অফিস থেকে করতে পারবো না, আপনি একটু ফার্মিয়নটা খুলে দিন। হ্যাঁ okay. So now z square plus 4, this you can write it down as what? You can write it down as z minus 2i cube and z plus 2i cube, right? Now you can see that this factor and this factor will cancel. So you will have only this thing, and you have to differentiate that. You just differentiate it 2 times. So if you carry out the differentiation, this will be 1 by 2 limit z going to 2i. So ddz of, if you differentiate this, what you will get? You will get minus 3 divided by z plus 2i to the power of 4. Differentiate once more, then you will get minus 4. So this will give us 12, and this will be 5. and d dz is gone. And now you just need to take z is equal to 2i. If I take the limit z is equal to 2i, just put z is equal to 2i at this point, then this, okay, this 2 and this 12 will cancel, so we will get a 6 divided by 2i and 2i, this will give us 4i to the power of 5. And now you can just, so I to the power of 5. So that is basically I4 into I square is -1, therefore I4 is 1, so I5 is I. So you have I here, and so you will have minus I 6 by 4 to the power of 5. So that is 2 to the power of 10. So you can just calculate what this is. 4, 6, 8, 16, 32, 64, 12. So you just calculate this. I think I've done it correctly. So this will give us minus 3i by yes. So this will give us minus 3i by 512. So let us end the class here for today. You just go through the examples that I have discussed. You also go through the theory of residues that I have told you, and then we shall continue from here on Monday. So let us end the class here today. If you have any doubt, just send me an email. So let us finish it here. Thank you very much for today.